Start with these two examples here. One, we're taking a ketone under basic conditions, and in the other one, we're taking an ester and using basic conditions. All right, and just to make sure everybody's sort of thinking in the right place here, when we start out with this ketone, we get this aldol addition reaction. And if we start out with a ester, we get a Claisen condensation reaction. And remember, we talked about making our lives a little bit easier here, making it easier to see what our product is. Since these reactions are going to happen between neighboring molecules, we're going to draw down both of them. One of them is going to be playing the role of the nucleophile, specifically at which site? At alpha carbon. And the other one's going to be my electrophile, specifically at what site? That carbonyl carbon. All right, and nucleophiles attack electrophiles. Okay, so we'll talk about our products here. I want everybody to take a second and to identify what our intermediate is in this reaction. We have one of them playing the role of the nucleophile, the other one playing the role of the electrophile. When my nucleophile attacks my electrophile, we get this intermediate. We even got a special name for it based on its geometry, that tetrahedral intermediate. All right, and the key to understanding the difference between these two reactions is looking at those different tetrahedral intermediates. Excuse me, hang on. I'm going to kind of do like a lazy man's mechanism here, where I kind of skip that first step and just jump to that enolate ion. And then I'm going to show my nucleophile attacking my electrophile, and that pi bond jumping up onto that oxygen. That will give me my tetrahedral intermediate. All right, so I'm going to have this new bond, that bond formation arrow, between my nucleophilic carbon and my electrophilic carbon. My electrophile has these 5 carbons here. So I'm going to need to decorate that electrophilic carbon. So I have a total of 5 carbons. All right, and I'm spacing it out like this because I know that I have to have that carbon-oxygen single bond with that pair of electrons on that oxygen. All right, so here's my tetrahedral intermediate for my aldol addition reaction. Connecting this 5 carbons to this 5 carbons, specifically the alpha carbon to the carbonyl carbon. I can play that same game with my Claisen condensation reaction. All right, again, I have these two esters here, where one of them plays the role of the nucleophile at the alpha carbon, the other one the electrophile at the carbonyl carbon. All right, again, lazy man's mechanism here, skipping to the important step. We're going to have that nucleophilic attack, giving us our tetrahedral intermediate. All right, based on what we just did, I want everybody to take a second and draw me my tetrahedral intermediate. All right, so here's my tetrahedral intermediate for my Claisen condensation reaction. Again, I have that new bond between my alpha carbon and that electrophilic carbonyl carbon. All right, and let's look at these two side by side here. All right, so this is our aldol versus Claisen intermediates. All right, again, I said looking at these intermediates, thinking about our mechanism is what's going to help us understand the difference between these two reactions. All right, so let's put them side by side here, our aldol intermediate and our Claisen intermediate. All right, and at first glance, they look very similar. They are very similar, okay? But there are some key differences here. There's actually one key difference here. All right, it's playing the spot the difference game. What's the difference between these two intermediates? The oxygen, right? My ester has these oxygens in there. And the important one is this one right here, the one that's bonded to that formerly carbonyl carbon, my electrophilic carbon. Because in both cases, we have this angry oxygen with this net negative charge, all right? Oxygen would love to get rid of that net negative charge. Over here on our aldol side, though, my carbonyl carbon, or what used to be my carbonyl carbon, is bonded to 3 other carbon atoms. And carbons are terrible leaving groups, all right? So my aldol intermediate has no leaving groups. Over here on my Claisen condensation intermediate, we're not bonded to 3 carbons, we're bonded to 2 carbons, but we also have this electronegative oxygen here. It is not a great leaving group, but it is still nonetheless a leaving group. So our Claisen condensation intermediate here does have a leaving group. So with our aldol intermediate here, since it has no leaving groups, it's stuck and can only be protonated. Since our Claisen intermediate here has a good leaving group, it's not stuck, we can kick off that leaving group. right, so just to finish this off here, our aldol product, we're stuck with our oxygen here. All we can do is protonate it to form that alcohol group. All right, so this is my aldol product, an alcohol, and it's not an aldehyde, it's a ketone, but nonetheless, that's where the name comes from. All right, in our Claisen reaction, this thing is not stuck. Our tetrahedral intermediate, that pair of electrons can come back down and kick off that oxygen. So this then reforms that carbon-oxygen double bond. I get this carbonyl group in my product. I get a second carbonyl group in my product. All right, so again, if we just want to stack them next to each other so we can see here. My aldol intermediate, because it doesn't have a leaving group, that oxygen is stuck. All I can do is protonate that oxygen. In my Claisen intermediate, now I do have a good leaving group. So that pair of electrons will come back down and kick off that leaving group, reforming that carbon-oxygen double bond. All right, so here is my aldol product in aldol versus my Claisen product with these two carbonyl groups. In both cases, since my alpha carbon was my nucleophile and my carbonyl carbon was my electrophile, I get this same 3 carbon spacing, one of those double checks we can do for these reactions when we're predicting our products. All right, but I do get a different functional group on what was formerly that electrophilic carbon. All right, again, the key here being that intermediate. Okay, one other thing that I can ask you about with our aldol additions here, or I guess it wouldn't no longer be an aldol addition, but what we would call an aldol condensation, is if I took this exact same setup here, but I applied heat. All right, what we get is our aldol addition, but because of that heat, we then get this last dehydration step. All right, everybody take a second, see if you can't predict our products here for what we call an aldol condensation. All right, so in my aldol condensation, I no longer have a hydroxyl group. I no longer have an alcohol group. What's my other functional group in my product for the condensation? Alkene, carbon-carbon double bond. And that carbon-carbon double bond is specifically going to form conjugated, right, perfectly spaced to my carbon-oxygen double bond. This is going to drive me nuts looking all ugly like this, so I'm going to fix my bonds. All right, I don't lose any carbons here. I still have that 5 carbon fragment. Boom. All right, so our condensation reaction is where we do our regular aldol addition. but then use heat to follow that up with a dehydration reaction. It turns out that these dehydration products, we have a special name for these. They have a carbon-carbon double bond, so ene, and a ketone, so one. These are enones. All right, the addition reactions all by themselves, because they occur at low temperatures, turn out to not be hugely efficient, like 30% yield, something like that. Our condensation products, though, our enones, because you have that application of heat, very much so an efficient reaction. And we're going to see next class period, like the last unit, or rather last section of this chapter, is going to be using these enones as reactants. They turn out to be pretty cool in and of themselves, all right? So these products that we get from our aldol condensation reactions, doing our addition, but then adding heat to do a dehydration, gives us these enones where we have this carbon-carbon double bond conjugated to our carbonyl group. All right, and then last thing I can throw at you here, if we have a dione here, what would a dione be? What's a dione? Two of them, two ketone groups. All right. If those two ketone groups are spaced perfectly apart here, we can get an internal aldol addition or condensation reaction, depending on our conditions. What do I mean by an internal aldol addition or condensation? What's that word internal going to mean? Yeah, so inside, so within itself, all right? So in this reaction here, you're going to have one of these carbons playing the role of the nucleophile, your alpha carbon, and one of these carbons playing the role of the electrophile, your carbonyl carbon. And the reason why this reaction will occur in this internal way is because we have this perfect 1, 2, 3, 4, 5 carbon spacing between my nucleophile and my electrophile here. All right, so these internal aldol condensations will happen when we have a 5 or 6 carbon spacing between our nucleophilic site, which is what in these reactions? The alpha carbon. And our electrophilic site in these reactions is what? Carbonyl carbon. We'll get this internal aldol addition or condensation reactions. I mean, I guess we got to be good here. We have to have our base. All right, but I want everybody to take a second and predict our products here. Again, to do our lazy man's mechanism here, we're going to show that nucleophilic alpha carbon attacking that electrophilic carbonyl carbon. right, so I'm going to have this new carbon-carbon bond. Obviously, I'm not going to draw it like this. That would be ridiculous. What do we get as our product here? A ring. All right, and so we kind of talked about this when we were doing our Diels-Alder reactions. The easiest way to draw your product here is to start with that ring. I'm going to have a 5-membered ring. And I'm just going to keep track of my carbons by numbering them here and then decorating them the way that they need to be decorated based on our reactants. All right, so for example, on carbon 2, I have that ketone functional group still. That didn't get touched in my reaction. Carbon 5 was that electrophilic site, so it's now got a carbon-oxygen single bond, which gets protonated to form an alcohol group. And what else am I missing on carbon 5? That other carbon over here, my methyl group. So why does this reaction occur only when we have this perfect 5 or 6 carbon spacing? Because we get these cyclic structures. Remember, you talked about the stability of rings, 3 and 4 membered rings, like never going to see them really, very unstable. Anything bigger than 6, you'll see sort of out there in the wild, but they're just not as common. They actually tend to be higher energy, or they are higher energy than 5 or 6 carbon rings, right? 5 or 6 carbons is kind of the sweet spot in terms of ring stability here. So these internal aldol addition reactions will form these rings. And if we went ahead and took this and applied heat, we would get that condensation product. Everybody take a second and give me my condensation product. All right, looking at my carbon numbering here, where is my new carbon-carbon double bond going to go? Between carbons 1 and 5. Right, so that it is conjugated to that carbonyl group. Still got that methyl group on there. Cool. All right, so then we moved on and we were like, all right, great. So this is how you would do an aldol addition, condensation, or a Claisen if you just wanted to have one of your, rather, if you just had like one ketone that you were trying to react with itself. But what if we're trying to have these mixed aldol or mixed Claisen reactions? All right, so these were our mixed aldol and Claisen. For that, we had to first create our enolate ion and then afterwards introduce our electrophile. All right. So in order to create that enolate efficiently, we got to add some super strong base. And there were 2 super strong bases that we were introduced to, sodium hydride and lithium diisopropylamide, or LDA. Everybody's going to take a second and remind ourselves what we needed, what the difference is between these 2 bases applied to this same ketone here. So the key here is I have these 2 alpha carbons that are not identical. One of them is less substituted, so it's more accessible. The other one is more substituted, so it's more stable. All right. Our LDA is our bulky base, which will favor the more accessible carbon, specifically deprotonating that orange alpha carbon. And the other one, the sodium hydride, is teeny tiny. So it's going to prefer the more stable or the more substituted enolate, specifically deprotonating that green alpha carbon. All right, so why is this? We've actually seen a similar argument before when we were talking about electrophilic addition to conjugated diols. And we're going to illustrate this using an energy diagram here. All right, both of these curves will start at the same place. They have the same reactant. But what happens in the middle and what happens at the end here are different. To be clear, my color coding, I tried to make the same here. So in orange, I have that LDA, and in green, I have that sodium hydride, specifically deprotonating that more or less accessible carbon. All right, when we look at these diagrams here, there's kind of two pieces of information that we get. One, we get by looking at the middle of the graph. The other, we get by comparing our starting and ending points here. All right, so what does our middle of our graph tell us? What do we call this barrier here? So this is our activation energy. All right, and what does the height of that barrier tell us? We see this orange one's a smaller barrier than the green one here. All right, what is that telling me, comparing these two reactions? So less energy, and specifically corresponding to the energy that I need to jump over this hump here, my activation energy. All right, so this corresponds to what we call the kinetics of our reaction. And by kinetics, I mean what? Speed of the reaction. Yes, kinetics is how fast or slow a reaction occurs, right? This orange reaction, what? Happens faster or slower than the green reaction? Faster, because it's got a small activation energy barrier. So the LDA here, rather deprotonating that more accessible carbon, this is what we would call our kinetic product. All right, our kinetics is the information we get from the middle of the graph here. All right, in green I have my sodium hydride, and I can see that that's a slower reaction, right? It's got a higher activation energy barrier. But then I look over here at the end, and I'm comparing now my products of these two reactions. All right, and which one of these is going to be more favorable, the orange or the green product? Green, why green? Lower energy, right? Lower energy is good in chemistry. We like low energies. So this green product here is more stable because it is the lower energy product. All right, this is what we would call the thermodynamics of the reaction. So this more accessible carbon here is our thermodynamic product. All right. And what energy is required to jump over these activation energy barriers? Thermal energy. So we can help tune this reaction in one way or the other by changing our temperatures. That's why we would use LDA at low temperatures. So there's not very much thermal energy to jump over this higher activation energy barrier. It jumps over the low one and then gets stuck over here. If we want it to be able to jump over that large activation energy barrier, we need to crank up the temperature. So that's why we would use sodium hydride at high temperatures. All right, so we can tune which one of these enolate ions we're going to form, whether we're going to form the less substituted, more accessible one with LDA at low temperatures, or whether we're going to form the more substituted one at high temperatures using our small base. And these are both ways of just creating enolate ions, creating our nucleophiles in our reaction. All right, so let's just take one of them here and do all the things that we can do with it. So let's take our butanone. All right, we're going to treat it with LDA at low temperatures. And so that's going to specifically deprotonate which one of these two carbons? The one on the left or the one on the right?
Right.
The more accessible one, right? So this one over here is going to become my nucleophile after that first step. Since I use this super strong base, I've converted all of my ketone into this nucleophile. So now I'm going to toss in an electrophile. All right, so first we're going to look at what happens when we use an alkyl halide here. All right, I want everybody to try to predict our products. We have our enolate ion nucleophile. This alkyl halide is our electrophile. I want you to think about which site is your electrophilic site, and then do what nucleophiles do, have it attack your electrophile. All right, so this is our electrophile. What is our electrophilic site here? Is it the halogen? No, the halogen plays what role? That's our leaving group. And it gets kicked off from that electrophilic carbon that is bonded to that leaving group. So my nucleophile, attacks my electrophile, kicking off that leaving group. So this is a way to form a new carbon-carbon double bond, specifically to alkylate that alpha carbon, right? So we have our original, let's just color code to keep track here, our original 4 carbons from our nucleophile. Here's my nucleophilic site. I'm going to draw that new carbon-carbon bond, what lives on the other side, my electrophilic site, and my electrophile has that total of 3 carbons I need to add on. So there's 1, 2, 3. Okay, so we turned our ketone into an even bigger ketone, right, by alkylating that alpha carbon using a, what the heck are these? Blanket. Alkyl halide, geez. All right, so that's one electrophile that we can add. I guess we're going to be good here and include that last acidic workup step to kind of neutralize our strongly basic conditions here. Let's take that exact same nucleophile, our exact same ketone. We're going to do that exact same first step where we deprotonate that alpha carbon with LDA. But now we're going to add in a different electrophile. All right, we're going to add in another ketone here. right, we'll add in acetone. And then I'm going to do the same thing, but instead of adding in another ketone, I'm going to add in an ester. And everybody's going to take a second and predict the product of these two reactions here. Again, we made our enolate, our nucleophilic carbon, specifically that more accessible one since we used LDA. All right, so in both of these cases, my electrophile is that electrophilic carbonyl carbon. All right, but the difference here is going to be my intermediate that's created, my tetrahedral intermediate. All right, this is exactly what we were discussing when we compared side by side at the beginning. All right. I don't know where it went. Oh, here we go. Our aldol reaction, rather when we react with our aldehyde or ketone, we're going to get this aldol intermediate here that has no leaving groups. These aren't leaving groups. If we react it with an ester, though, we'll get this tetrahedral intermediate that does contain a leaving group. All right, so in the case of my ketone, since there's no leaving group, I'm going to have not only those 3 carbons from my electrophile, but also my formerly carbonyl oxygen, single bonded, giving me that alcohol group, my aldol product. All right, when I get to my ester though, it's got this leaving group right here. So my new carbon-carbon double bond to my electrophilic carbon. What's the functional group on that electrophilic carbon over here on my ester, when I use my ester? What am I going to put here? Yeah, so not an alcohol group because we had this leaving group that got kicked off, allowing that carbonyl bond to reform. All right, so to be clear here, when I use a ketone or aldehyde, that's when I get that aldol type reaction. Whereas if my electrophile is an ester, I get that Claisen type reaction. And we're going to be good. Our last step here is that acidic workup. So let's add in that 3rd step just to complete things here. All All right, so same nucleophile because we treated that nucleophile with that same bulky base. If we use a alkyl halide, we just get a simple alkylation reaction. We've added on a bunch of carbons. If we use an aldehyde or a ketone, we're going to get an aldol type reaction, giving us our aldol product. And if we use an ester, we're going to get a Claisen type reaction, giving us our dione, right, where we have those two carbonyl groups in our product. All the same nucleophile, that a nucleophilic alpha carbon, just treating it with different electrophiles here, that different second step. All right, that's all I got for you.